Okay, welcome everyone to the session 6. And today our objective is to look at machine learning overview, the key concepts in machine learning, and we'll start with the regression modeling. So in the last 5 sessions, we have gone through basic statistical inference, and we also have gone comprehensively through EDA, exploratory data analysis, and this is the logical next step. And I'll talk about what exactly is machine learning, what are different machine learning problem types, and then we will deep dive into one specific problem type called regression problems or regression modeling. If we compare with the traditional rule based on expert systems, for example, before machine learning, most people were developing systems using rule based systems, which were also known as expert systems. For example, let's say organization was developing a fraud detection system, right? So what they would do, there would be a domain experts, right, who would have gone through the fraud transactions and would have understood the rules, right? So given these conditions satisfy, right, or the transaction has this kind of attributes, then it would be called fraud or not a fraud. So this knowledge base would have been developed or evolved over a period of time, and there will be domain experts which would have understood over a period of time and collected into a knowledge base, and those would be actually used or leveraged to create rules, and those rules would typically be fed into rules engine, right, and to the system. So if they develop a fraud detection software system, right, those rules should be configured or explicitly written like if else rules, right? If this condition else, if this condition satisfies, it's a fraud, else it's not a fraud, right? So there were several systems developed with this particular idea and very popular in traditional systems. And then when a new input comes like a transaction data, right, with all its attributes, and it will go through this rule based engine, and then we'll take a decision saying that it's a fraud or not a fraud. Okay, and these were very deterministic systems. So it will very confidently say it's a fraud or not a fraud. Okay, so it's not a probabilistic system. And of course, as the rules change or the context changes, the experts again add rules or remove rules from the system, right? But this happens very slowly because manually understanding this changing context, okay, takes a lot of time, and then configuring them manually also takes a lot of effort and cost. So some of the limitations of this system is of course manual input of the rules, and adapt to changes is extremely slow, right? It cannot quickly adapt to changes, very time consuming, and configuring very complex pattern, right? To identify complex patterns is also a kind of a challenge in this kind of systems and difficult to maintain. So over a period of time, there'll be hundreds of if else rules, and it will be very difficult to kind of maintain those manually, right? So the two key challenge of course is adapt to changes, because today if you look at the business context changes very quickly, right, and organizations want to adapt to the changes as soon as possible to eliminate risk. Especially if you look at a fraud detection, it's possible that new fraud patterns might arrive very soon, every not 48 hours or every week, but these systems take months to adapt to those changes. So to eliminate risk, today organizations want a system which can adapt very quickly. So the alternative to this is of course your machine learning systems. In machine learning systems, what you have is you start with the data, right? You have historical evidences of what is a fraud and what is not a fraud, right? You collect those samples. So this would be the samples of both the classes in terms of fraud detection, if you say. So this will be contain fraud and non-fraud transactions, right? And then of course this will be the historical evidences, and what kind of sample or data set you will create will depend on the problem scenario, right? We'll look at some of the problem scenario in the next few slides. And then what you do is, your objective is to identify a pattern in the data, right? Which typically we call it a model. So one of the most key component input is basically your data, and then the output is basically a model. So we believe that there is some evidence or some pattern there in the data which can be captured as a model, right? And what exactly is a model? Typically a model is nothing but a mathematical expression, right, of the pattern evidence found in the data. So you can say the fraud or not a fraud, right, is a function of certain attributes of the transaction. So this is what we'd like to retrieve from the data. And who does that? The third component, basically your learning algorithm. So the learning algorithm, which is the most important component here, it can be a statistical learning or machine learning or deep learning. Now these algorithms, they iteratively go through this data, okay, and see if there is any particular evidence that consistently found in the data, and then it'll spit out the model from that. So the three core components of machine learning: one is of course your input, which is your data, and then your output, which is your model, which is nothing but think like a mathematical formula which comes out of the data. And then who does that? Basically your learning algorithms, right, which is the third most important component. So of course in the next few sessions we will explore all these three aspects. Data, we have already gone through certain aspects of inference and exploitative data analysis. Now we will deep dive into what are different algorithms and what are different models possible, okay? And these systems are designed to adapt to changes. So what happens is, when you create a function and a model, of course it captures the evidence that is there in the data, but when the new evidence or new patterns emerge, you can always add those evidences to the data and rebuild these models and deploy it, right? So going back to the previous slide, if you have a system, right, if you have a fraud detection system, right, and you learn from the data. Let's say you have a fraud detection system. So this model would be fed to the detection system, and when you get a new input, new transactions data, right, this will actually predict it is a fraud or not a fraud. But these systems do not predict confidently, deterministically. They'll say what is the probability that this is a fraud or not a fraud. We'll come to that in little more detail when we come to a specific problem. But what happens is, sometimes this function or this model also fails. So some of the transactions which it detects as a fraud can be actually not a fraud, and which it detects not a fraud can also be a fraud, and those gets captured as the user reports. Imagine that the user which initiates a transaction, and the transaction is approved by the system, but the user later, maybe after a few hours or a couple of days, reports back saying that there is a fraud transaction that has happened on his credit card or account. Then what happens is, those data points would again come back as a new data or new samples or new examples. Again the learning algorithm will rerun, right, and create the models. But how the whole thing happens, we will go a little more detail later. We'll first look at, of course, the first iteration. Imagine that you have the first version of data D0, and we create a model M0 out of it. right? But the adoption can happen very quickly, right? You can always keep on adding delta D, and which will actually give a model M1. And you can also depends on the kind of mathematical expression or function that we use. Sometimes it can be it can be a simple function, or can also be a very complex function, like a non-linear function, right? Which can actually encompass a very strong pattern in the data, right? So it can actually identify a complex patterns, and which can be deployed to identify complex scenarios also. Unlike rule-based systems, which typically we cannot explicitly code complex rules into the rule-based systems. Okay? So this makes machine learning an alternative and very popular compared to the traditional rule-based or expert systems. Now, if we actually talk about AI, which is a broader umbrella or a broader landscape, so any technique that enables computer to mimic human behavior, right? So in this case, also identify something is a fraud and not fraud. It can be compared to that. So even rule-based systems also kind of AI systems. So traditionally, even rule-based systems were also called AI systems because it had the ability to take a decision, right? But it also contains non-rule-based systems like a machine learning systems. So machine learning system is of course a subset of all AI kind of systems. So machine learning is ability to learn. It's very important. Learn from where? Learn from mostly the data without explicitly being programmed. So your rule-based systems are explicitly being programmed. You're saying if this, else that. But we don't say that in a machine learning system. Okay, so we automatically learn without explicitly being programmed. So that's basically a machine learning system, right? And machine learning systems of course have been there for very very long time, like 40-50 years, right? Several algorithms have been developed over a period of time. And but traditionally machine learning systems were mostly focused on structured data. When you say structured data, it's primarily means tabular data, right? So data that can be arranged in terms of rows and columns, right? Features, outcome, and samples, and all that. But of late, of course, people also try to find patterns in a unstructured data, especially images, right? NLP, natural language processing, or speech recognition, right? Very, very popular, getting very popular. And we are with later, of late, we have seen Chat GPT, right? Which where you can communicate with the natural languages, right? So your traditional machine learning systems are typically not capable or not very accurate to identify these patterns in the unstructured data. So that's where deep learning comes in. Okay, deep learning is of course a subset of machine learning. Mostly we follow the very similar concepts, most of the matrices, right? But the algorithms are different. This is primarily based on artificial neural network. So in some of the future courses, I'm going to cover deep learning, but the focus here is basically machine learning. So as a foundation, you have to understand machine learning, and then you can go to deep learning. Now, let's look at one simple example that we have already been discussing, the resale price prediction of used cars, right? The sellers upload the information about a car, and the buyers would search and buy those cars. So here, can we create a feature, right, to automatically estimate what is the expected sale price of the car? We have already gone through this in detail. So so here, if you look at the data set here, this is structured data, and we have already seen these are different columns and all that. Like we can predict the price of a car from different factors, right? So this is basically your data set, And let's get familiar with certain terminology. For example, each record or each row is basically called an example or observation, and each of these columns are called factors or features or independent variables. I'll of course come back and explain why they're called independent variables. And the outcome variable which we are trying to predict. Here the price would be my outcome or target or dependent variable. Right? So lot of machine learning problem types would be, we will have a data set. So historically we would know how the factors have influenced the outcome. Okay, so we will have evidences of different factors and features and how it had influenced the outcome. So in this case, different attributes like location, fuel type, transmission, how it actually influenced the actual sale price. And now what we'll do is, from this data set we are going to build a function saying that price, right, as a function of location, fuel type, transmission, and so on and so forth. We will learn a function. So this basically is a model. So these problems are called supervised learning. These problems are called what? Supervised learning. Because this is again a subset of machine learning. It's called supervised learning, in which we have the evidence of both the factors and features which has influenced the outcome and what was the outcome. So you can think like we had the information about x1, x2, x3, and xn, and what is the value of y. And we are trying to build a function called y is a function of x1 to xn. These are called supervised learning algorithms. There is also a class of algorithm which is called unsupervised learning algorithms. Again, we will explain and understand that a little later. So let's look at some of the examples of supervised learning ML problems. For example, predicting the sales revenue or volume, anything is fine, of a company based on previous sales data of a company for the next quarter. So what would be the expected sales revenue for the next quarter, right? This could be also a ML problem. Predicting maximum temperature in the next 24 hours based on the current wind speed, humidity, or atmospheric pressure, or any other parameters, right? This could also be a machine learning problem. Predicting expected change in price of a stock ABC the next 3 months. So what is expected gain or expected loss in the stock? This can also be predicted. Predicting if an employee will leave or not leave. This can also be a different kind of problem, right? Machine learning of an organization in the next 6 months based on different behavioral parameter of the employee, right? How satisfied, what's the appraisal of the employee, how many hours the employee is working, right? Or any other parameters that we can take into account. Predicting if it's going to rain more than 10 mm or not, right? It's going to rain more than 10 mm or not. So yes or no, okay, in the next 24 hours can also be a machine learning problem. Or predicting if a customer will buy or not buy a specific product, that's a high value product, can also be machine learning problem, right? So these are different examples of machine learning problems, and all of them are supervised learning algorithms, supervised learning problems. Because for most of these problems we need some historical data, and we would have evidences of how different factors has influenced the outcome, and based on that we'll build a model and then predict that in the future. But if you look at the outcome itself here, the outcome variable, right? For example, here it's a sales revenue, it's a maximum temperature, it's a change in price, that's in percentage of change, or a leave or not leave. So these are actually outcomes which are numerical values or continuous values, right? But whereas leave or not leave, it's not a continuous value, it's a categorical value. or categorical feature. Rain more than 10 mm or not. If you want to predict how much rain, it will be numerical value. But whether it is going to rain more than 10 mm or not, then it's going to be a categorical value. Yes or no. By or not by, categorical. So even in supervised learning algorithms, some problems where you're trying to predict an outcome which is continuous or numerical in nature, in certain problems the outcome is categorical in nature, right? So there are two different supervised learning problems, and I'll come back to the other slide later. So all the machine learning problems, which is we have understood that its ability to learn without being explicitly programmed, are categorized into supervised and what? Unsupervised. And supervised problems are problems where we have the information about the factors and the outcome, right? And then from this historical data or historical evidences, we are trying to build a function y equal to a function of x1 to xn. So these are supervised learning problems, but there are two scenarios where y can be continuous or numerical and y can be categorical. So now based on that, supervised learning problems are again categorized into classification and regression. So classification, predicting a level means basically your outcome, which are categorical. For example, customer churn or fraud detection, right? The transaction is a fraud, not a fraud. Customer will churn or not a churn, right? And in regression, predicting levels which are continuous in nature. For example, sales volume or a stock price prediction. So there are two kind of problems. One is classification and one is regression. And in classification also, there are two different types. Classification can be further divided into, one is called a binomial classification and the other one is called multinomial classification. So binomial problems where you are categorizing into two different categories: fraud, not a fraud; by or not by. They are called binomial problems. There can also be problems which are multinomial in nature, where we have to predict if it belongs to one of the classes out of n different possibilities. And one of the best example is basically given a text, right? Given a text or review, can you find out the emotion that is expressed in that particular review or text? It's a positive or negative or neutral, right? So this can be a multinomial problem. So classification problems are divided into two different types. Similarly, there is another class of algorithms, which of course we'll dive a little deeper later, but I'll just give a simple preview. Unsupervised problems are where we don't have the knowledge of y. We only have information about x1, x2, x3, up to xn, and different variables. And now within that, we have to find if there's a hidden pattern or structure in the data, right? And we can leverage that to take certain decisions. So there are two different classes of algorithms, are called clustering and one is called what? Dimensionality reduction. Okay, what exactly they are, I think we will leave that for a moment, and later when we come to specific problem type, we'll explore that in detail. So overall, all machine learning problems can be categorized into four different types: classification, regression, which are supervised problems, clustering, and dimensionality reduction. Four different problem types. And in fact, if you look at one of the most important library, so let me show you, that we'll be using, called sklearn. So if you search sklearn, give me a second. So scikit-learn is going to be the most important library when you're doing machine learning problems, right? And if you look at scikit-learn, this is a machine learning in Python, one of the most widely used library in Python. It has a six core modules. Six core modules. One module is dedicated for all classification problem types, which basically says identify which category an object belongs to, and then of course there are algorithms which can solve these kind of problems. Then there is a module which focuses on what? Regression problems, predicting a continuous valued attribute, right? Again, several algorithms which can address this problem. Then there is a clustering, which is a unsupervised, and a dimensionality reduction. So four different problem types, the four different modules. Then there are of course two more modules which are primarily dedicated for the model selection. So how to validate a model, right? How to compare models performance and all that, which is of course used as a part of the model development process. And then there is a module for pre-processing of the data. So some of these algorithms will need a specific kind of pre-processing, and those feature extraction and normalization, right? So those kind of pre-processing can be done, and there's a module for that. So if you look at also the way the library is also designed, okay, it's a dedicated module for different kind of problems: classification, regression, clustering, and dimensionality reduction. And these two modules are primarily for the model development process, okay, which can be leveraged across all these four different problem types. Okay, sorry. Typically, in a supervised learning algorithm, what we do is once we collect the data and explore, right? This is like a full data set, and we normally split the data into two different sets, randomly split. Okay, randomly split. One we call training set, and the other one is we call a test set. Of course, there are advanced validation methodologies are there, like a k-fold cross validation and all that, which we will explore later. But to start with, we will stick to the basics, and then we'll come back to the complex methodologies. So we'll split that into two different sets. Of course, the data will contain the set of features. You can think like it's x1, x2, and xn and all that. And this is y value. So two different splits, train and test. And we will leverage the train set, which typically is a larger subset. Okay, the different split ratios are there. We'll come back to that again. We'll take the larger set and build the model. So now you can imagine like this is basically your x train. Think like this is your x train, the x values of the training data, the feature set, and this is your y train, the corresponding y value, the outcome of the training data, and this is your x test, and this is your y test. Okay, irrespective of y is numerical or categorical. In both the cases, we will follow the same approach. And then we will build a model, let's say M0, from the X train and Y train. So this would look like something like, Y train, right, as a function of what? X train. So this is the model that we are going to build. And then to understand how good or bad the model is, right, how well it's performing, we have to take this function of the model and then ask the model to predict the y values for this test data. So you can think like you will take the function and ask the function to predict on the test data, which will of course predict its own y values. Let's call that y pred. These are predicted values from the x test. And because we already know what was the actual outcome of the y value, then we'll take and compare this predicted value from the function with the actual value of the y. Because we already know, that's the whole purpose of keeping a test data aside, to kind of evaluate how this function that we will learn from the training data, how well it is performing on the data that it has not learned from during the process of model building. And then when we compare it, right, it gives you certain metrics. Okay. So statisticians have defined certain metrics based on the problem type, and this gives us some insight into how good or how bad the model is, right? Of course, if it's a good, you can take it forward and deploy it. If it's not good, not as expected, then of course there's a multiple iterations that you can do. We'll discuss that during the process of actual model development. So quickly, so once we collect the data and data set, we have already explored and cleaned, removed outliers, imputed missing values as required, which we have gone through in the previous sessions, right? We'll split the data into train and test, build a model, validate against the test data, and measure metrics. That's a typical process that we follow when we do a supervised machine learning problem. Okay, so we have already focused on these two parts, some of the problem formulation also. Of course, this will be keep coming back again and again. So today and the next few sessions, right, we will keep focusing on these two, right? So we will actually look at how to build models, build machine learning models, and how to validate and evaluate models. Okay, and these two sessions, of course, will keep it for future sessions. These two modules. Okay, so now let's what we do is we'll jump into our problem, which is predicting the resale value of the used car, and we'll look at a regression modeling. So next three sessions we will be mostly spending around regression, and then we'll come to the classification problem. So to do this, as we do earlier, we'll go back to our GitHub location, and I have uploaded a notebook, right? If we go to GitHub location, ML course v1, let me put that again on the chat window in case. And I have uploaded the files into session 6. So this is the file, data file, final cars maruti.csv, which was an output of our EDA. I think in the session 4, we'll be actually leveraging that to build a model. So I have also uploaded a worksheet, and we will work through that. So if you can load that, regression used car price worksheet v1 IPYNB. Let's go over this example now. So like last time, we will also look at live coding. I'll give a minute here for you to kind of load the data, load the notebooks. And once you're done, you can just say done or yes on chat window. So this data set, as you have already seen, it contains certain attributes of the car, used car, like what is the model of the car. And this is of course only the manufacturer of Maruti we have taken. Can we predict the resale price of a Maruti car given that we know information like what model it is, which location it is up for sale, what's the age of the car since the car has been bought, how many kilometers driven, what's a fuel type in terms of petrol or diesel. We don't have any other information. I think mostly we have petrol and diesel. Transmission, whether it's automatic or manual, whether it's a first owner, second owner, third owner, and so on and so forth. What's the mileage it gives, what's the power in terms of bhp, number of seats, which also tells whether what kind of car it is, and the price at which the car was actually sold in this historical data, right? So let's go ahead and load the data. So we'll say cars df equal to pd dot read csv. Final cars Maruti. We already done all this. Quickly look at first few records, and how many samples we have. We check shape, we have 1010 samples, 11 columns. Out of that, of course, one of them is price, which is my outcome variable here. So this is my dependent variable here, right, or outcome variable here. And these are my factors. You can say x1, x2, x3 up to x10. There's 11 columns, so 10 different variables are there. And let's look at first what we'll do is we will look at one variable and see how it is influencing the outcome, and then we'll expand that into multiple variables, right? Is it easier to understand and relate when we first look at one variable, and then we can expand that to all the 10 variables. So relationship between age and price, as you've already seen, both are numerical features here, age and price. So you can use something like scatter plot, data, cars df. My y would be, in this case, price, and my x would be age, right? And we can see from the data there is a downward trend, right? As the age of the car increases, the price reduces. It's a negative correlation. We have seen that already. And this is of course a discrete value. That's why it looks like this. Though it's a numerical, it's a discrete value. So of course our objective is to find how much it's decreasing. So every 1 year reduction in age, right, what is the reduction in the price of the car, right? So you can actually go and build a model, okay, based on these two variables. So this is basically called a simple linear regression. So there are of course various algorithms are there. So we'll first try linear regression. In linear regression, the assumption is that there is a linear relationship between features and the outcome variable. So the assumption is what? The price decreases linearly with the age. Of course, this assumption is correct or not correct, we'll understand when we actually evaluate the model later. But we can always start with a very simplistic assumptions and first build a model. Okay. For any regression model, it's always advisable that you start with a very basic linear regression, a simple linear regression, basically linear regression, and understand how the performance of the model is. So if you look at this particular line, the functional form of this line, okay, if you call this, let's say, x, and we basically call this y, right? The functional form of this line would be y equal to beta 0 plus beta 1 x. It's a linear model where beta 0, when the x value is 0, y will be equal to beta 0, isn't it? So that means the beta 0 is nothing but the intercept term. It's called intercept. Okay, the point at which the line intersects the y value when the x is equal to 0. This is called intercept term. The beta 0 is basically my intercept. And as the value of x increases now to 1, 2, 3, and 4, okay, how much the y value changes. So that's basically the change in y with respect to the change in x, the unit change in x value. So that's nothing but my slope or the coefficient. So how much the y changes with respect to the x value. So this is also called the slope or the coefficient, right? Coefficient. So for example, if we say my age is 8, that means we can say what is the intercept plus how much it changes multiplied by the age of 8, right? So that's a change we can add to that. So a simple linear regression. So y equal to beta 0 plus beta 1 x, and we call this y as a hat because whatever the value that we estimate from the model won't be exactly the y value. There will be some error would be there. So y is the predicted value of y hat, and beta 0 and beta 1 are regression coefficients. Now the question is, how do you even find the line? Because if you look at this points, the way they are scattered, we could have drawn several possible lines through those points, isn't it? Now, out of these possible lines, which is the what we call the best fit line, which we should take, which fits the points or data points the well. So because every line here, if you talk about the line L, L2, L3 and L4, everyone has a different beta 0, different intercept and different coefficient. So the best fit line here, the whole objective of building the model is, when you say best fit model or best fit line, okay, it should have the minimum error or maximum accuracy. Okay. The line which gives the minimum error between the predicted value and the actual value. For example, if you say, what is the value of the car when the age is 12, right? And of course, the line will predict the values here, but there are actual cars which have been sold at different possible values, right? So if you draw a perpendicular line to that, that will basically your error. So this is your actual y value, and what the line predicts will be the predicted value y hat. So y minus y hat will be your error. And the whole objective is, of course, to how to minimize this. Whether you should draw a line, the different slopes and different coefficients, which will minimize this particular error. And of course, we cannot minimize the error for a particular data point. We have to minimize the error across all data points. So what we do is, then we look at the error across all the data points, the summation of I equal to n. So all the n data points, like here you can think like all the 1010 observations, where my yi, the actual value of y, minus the predicted value of y, which is y hat, and minimize this. But here, if you take the actual difference between y and y hat, it might so happen that some values have a positive error and some value have a negative error. That means sometimes what you predict will be lesser than the actual value, and sometimes what you predict will be more than the actual value. So they will cancel out each other. So the two possible choices we have, either you take the absolute value of it or you take a square value of it. Right? So we'll deep dive into this particular concept a little later, but let's assume that we'll take a square value of it, which is called a squared error. The next session we will actually look at a little bit of deeper into why we're taking squared error. For the timing, let's assume that we take a squared error. That means the farther the prediction value from the actual value, we pay more penalty to that. And then we will have to average it across all the data points, right? So if you write it again, so 1 by n summation of yi minus yi hat, right, square. So this is called a squared error, and because we are taking the average of it, so this particular error is called what? Mean squared error. So whatever line that you draw, we can always calculate the mean squared error of that. So we look at the errors that we are getting from different data points and can calculate the mean squared error. So let's say this is a line L1 and we calculate the MSE of that. Let's call it MSE1. Similarly, we can, let's say, draw another line. We draw another line, right? So different lines are there, possible lines. And what you do is we say, though of course it's not done like this, but just for understanding perspective, every possible line has a different errors. Now out of that, if we have to choose which is the best fit line, now we'll choose the line which is what? The minimum MSE. The line which gives you the minimum MSE will be the best fit line. Among these three possibilities are there, right? So the best fit line will be the line which minimizes this particular error. But of course, there are not only three possible lines, there can be infinite possible lines that can draw through these data points. So how do we do that then? How do you find the best fit line? So do mathematically figure out, right? So basically say DMSE. So to find the minimum of any function, we can always take a derivative, right, with respect to the variables and equal to 0. I'll tell you why. Now if you look at this particular MSE, which is nothing but yi minus yi hat square, which of course we can expand. This yi hat is nothing but the predicted value, okay, from the line itself. What is the slope of the line and what is the coefficient of the line? So you can expand that what? Yi minus beta 0 plus beta 1 xi. So now if you look at the whole equation here, from the data we know what is yi, it's already given here, right, in the data, the price, and what is the xi, in this case age. This is my price given and this is age given. So different age, different price there, right? So now there are only two variables which can be changed. Beta 0 can be changed, beta 1 can be changed, right? And we will find the optimal value for beta 0 and beta 1. So if we change the beta 0, beta 1 value, because these values are given, we cannot do anything. We keep changing this, different MSE values you will get. So there is an optimal value for beta 0, beta 1 for which the MSE is minimum. So what we do is we take a derivative of this whole function here, MSE, with respect to beta 0 and beta 1, right, which is equal to 0. So of course the library does this. There are two different methodologies to do this. We'll dive a little deeper into this in the future session. One is called OLS method, which is nothing but ordinary least square method, right? This is also called a closed form solution. And there's another method called a gradient descent. So just note down these two as of now. Of course, we will go a little more deeper into this in the next session. And the beauty is, of course, the scikit-learn library, which automatically does this for you and gives you the optimal value of beta 0, beta 1, for which the MS is minimum. So here also there is a nice site there called MLU Explain for linear regression. Right, it's a very nice site, which of course shows an example of how the predicting the price of a house, right? Find the size of the house in terms of square feet. You can think like a carpet area or something, right? And you can see as the carpet area or a square feet of the size increases, the price of the house also increases. It's a positive correlation here, isn't it? So now, if you want to build a model, right? Let's say this is the line which predicts, depicts the relationship between the size of the house and the house of price of the house. Now, for this specific data point, where the house was sold, let's say about $550,000, right? Actual sold, but the model, if you use the model, will say the price, the house would be sold what, at, let's say, $350,000, isn't it? So this should be the error. This should be the what? The error. So that's basically the error for this specific data point, EI. Similarly, you can see you could draw a perpendicular line to the from the data point to the line. So those perpendicular lines would depict the errors. Some errors are positive, some are negative. So in this case, the price is underestimated. In this case, the price is overestimated. And if we, of course, we cannot optimize for a specific data point, we have to optimize for the overall all data points, right? So the error would be, total error would be, or average error would be minimized. So here again, the actual error is nothing but my yi minus yi hat. So this is basically a mean squared error. Okay, so what we'll do is we will go back now, look at how the model would be in our case when we predict the price, resale price of the car with respect to only age. So when you try to predict the outcome with just one variable, it's called simple linear regression, or SLR. But when you predict from multiple different variables, then it will be beta 1, x1, beta 2, x2 and all that. That's called multiple linear regression, which of course we'll try later. But we'll start with the simple linear regression. So let's first set x and y value. So my x will be what? My x will be cos df, and in this case I have chosen to be what? Age. And y will be my cos df dot price. So this will be my x and y value. And the first thing that we do is what? Even before we build a model, we cannot use the complete data to build a model. So we'll split the data set into two different sets. One is train and one is test. So the first step is typically, once you identify what are the factors and what is the outcome that you predict, you split the data set first into two different sets. So to do that, we have to take help of scikit-learn library. And if you remember, there is a module called model selection, which typically is used for model validation and all that. So there is a function called train test split, which you can utilize. And then What it does is, as you've already seen before, if you give a data set, right? Imagine you have a x1, x2, x3, and y. So what it does is it splits into two different data sets, right? So one will be your train and one will be your test. Of course, this does it randomly, not sequentially. And it returns four data frames. One is what are the x values of the train, what's the y value of the train, what's the x value of the test, and y value of the test. So you can name things like this. This will be my x train, and this can be my y train, this one. This will be my x test, and this can be my y test. So you can say x train, x test, y train, y test, right? Test train split, and say x, y, and train size 0.8. So this is the split ratio. So it's saying that 80% of the samples will be in the train data and 20% will be in the test data. Typical split ratio that we follow is 80-20 or 70-30. Again, the whole idea is you should have sufficient samples in the test data, right? Sometimes we also do 90-10 or 95-5 also, but those basically, especially when you have very large number of samples. Let's say you have 100,000 samples, 1 lakh samples are there. Now if you do a 90-10 also, there are 10,000 samples in the test data, which is a very good sample set to validate your model, right? If your data set is not very large, then typically you follow 80-20 or 70-30. Typical, the number of samples in the data set is in proportionate to the number of features that you are using, right? So the sample set, the number of samples in the data set, typically depends on the number of features. Is the number of features typically depict the complexity of the model, or complexity of the patterns that you're going to find out. If you have 10 features, vis-a-vis you have 100 features, right? When you have 100 features, of course you need more samples to depict those the features influence on the outcome. But what actually is the relationship? There is no straightforward answer, but we'll come back to certain assumptions little later once you've gone through a couple of modeling exercises. We can also do a random state here. Random state will ensure that the split that I get and you get would be exactly same. Okay, so this is the effect of seed value we have. Now if you look at the extreme shape here, now extrain has 808 samples, and X test also has the remaining 202 samples, right? So that has been split into 80 and 20 ratio. And if you look at some of the values of X test and X train, so like X train 0 to 5, so different age, and X test, right? And of course your Y train will also be same. So if let's say Y train, age and the price. Now the first thing that we'll do is what? We'll go and build a model. So we'll build a simple linear regression model. So from sklearn dot linear regression, linear model, import linear regression. So if I go back to my scikit-learn site now, if you look at, there's a module called regression. So under regression there are many different models out there. So there is a set of linear models. What we're trying is ordinary least square method, the first one. Okay, so of course there are quite a few different models are there. Of course can't explore everything, but we'll explore a couple of them. So linear model, there's also a support vector machine, nearest neighbors, neighbors, decision trees, ensemble methods. You can see there are 70 or 80 different types of models are there, right? We will explore, of course, linear model, neighbors, decision tree, maybe logistic regression, right? Some of these models will explore in this particular course, and then which will, of course, give you some idea about how these algorithms work, and you can, of course, you can learn on your own, or some of these other models will address in the advanced course. So if you come back here in the linear regression, the first thing that we do is initialize the regression model, linear regression model, right? And then LREG v1 dot. So all models have a function called fit. So fit is basically, you can say, best fit line, right? Basically asking you to, can you fit the line which minimizes the error. Fit to what? To this, basically my data. So given this is my x train and y train values, okay, so this contains my samples from I to n, isn't it? So 808 samples. So this is my age and this is my price. So you're asking to, can you fit a line to this data points? There's 808 data points, and the line should have minimized the error, which of course is encoded into this particular model. The moment you just execute this line, the model is already built. Okay, so whatever we have discussed so far here, right, it would have found the beta 0 and beta 1 value. Okay, this is the beta 0, beta 1 that minimizes the error, given these are the data points. These are 808 data points that we have, and these are the beta 0 and beta 1 values. So what are they? So the model will have those values. So LREG v1 intercept and LREG v1 coefficient v1 coefficient. Yeah. So it says that the intercept is 7.60 and the coefficient is minus 0.49, which says that the model looks like, right, it's saying that the price of the car can be estimated like 7.60 minus 0.49 multiplied by age. Okay, the negative sign here means what? As you have seen, as the age increases, the price reduces. The negative sign basically says that there is a negative influence of age on the outcome. Okay, we have seen that also because the negative correlation is minus. So if your car is, let's say, 10-year-old, you can say 7.60 minus 0.49 multiplied by 10 will be 4.9, and whatever that value here, right, 2.7 lakhs. That's the estimation, expected price, sale price of the car. Of course, the expected sale price won't be very accurate because we have taken only age into account. If we add other variables, the accuracy will increase. That we understand that. But from the perspective of understanding, we have taken just one variable to kind of first understand how this works. Then we'll go and expand on that. So this is basically the model, right? And this is your slope. So if you go back and look at our LM plots, we can also do something like SN LM plot. just to depict that. So cars df, my y equal to price, x equal to age. Okay, so there's a option called fit reg. Okay, you can set to true, and which says basically, yeah, this is the line. So that's a regression line. That's a best fit line. And you can see the intercept is about 0.76. I think that's about 0.7.6. And the slope here is about 0.49. So delta y by delta x would be 0.49. Negative because it's reducing. This is accurately found out by the LiDAR model. But how good is this model? What's a uh, how close it is compared to the actual sale price of the car? So can we go and predict on the test data? So what we'll do is we'll predict on test set. Let's say we call it ypred equal to lreg v1 dot, there's a function called predict. So every model has two functions. Irrespective of what the model is, the way scikit-learn is designed, it is very well abstracted. Irrespective of what the model is, it has two functions, two methods. One is called fit, which will train the model. This is called model training. Train the model with the training data. And then it will also have a function called what? Predict, which will predict or apply the model to the trained model, to the test data, and give you the predicted value of the y. So if I pass x test here, because I'm going to predict the value, that will give me the y pred. Now how close it is to the actual values? To do that, what we can do is we can actually create a data frame and first store all the details here. So you can actually create a data frame on the fly like this, pd.dataframe, and then pass a dictionary. The dictionary, what it should say, okay, let's say actual. We'll create a column called actual and store the value of the y, the actual value, which is y test, remember, and the predicted value of the model y pred. So you can compare 1 to 1. So one column will be actual, one column will store the predicted value. The other one we can call it error, or we also call residual. The error is also called residual. So y test minus y pred. So let's look at ydf dot sample, randomly sample some 10 records and look at that. And if you see here, these are the indexes of the cars which were in the original data, but they have taken out, kept in the test data. So you can see randomly they were taken out. So we have about 202 samples, if you remember, in the test data. And if you look at this particular car, which is sold at 5.18 lakhs, right? But the model is saying it will be sold at 6.61 lakhs. So this is of course overestimation. But still very close compared to the actual value. There's an error of what? Minus 1.43 lakhs. So here it's a error of minus 1.14 lakhs. 2.79 is very high error. But if you look at the other, some few other ones, like this is very close, 4.9 and 5.14. This is also quite close, right? But given we've taken only one variable called age, I think this is pretty okay, right? So this is actually your yi, the actual value of the car. This is what? This is yi hat, the predicted value of y, which is calculated based on the intercept and coefficient, and this is the residual. So you can think like actual y value equal to beta 0 plus beta 1 yi, right, xi plus error ei. Okay, so this is your nothing but by yi hat, and this is the error here. Of course, we cannot look at individual errors. We will what? Take an average of it. It's nothing but my MSc, if you remember. So we'll take all these EIs, right? We'll take all these EIs, EI square 1 by n. Because some are positive, some are negative. So we'll take the square value of it and take, and this is basically called your MSc. So let's look at MSc. To calculate MSc, again from sklearn dot metrics. So sklearn now also has a module called what? Metrics. This part of that model selection. Import mean squared error. So there are many different possible errors that you can calculate, but in this case we are only interested in what? Mean squared error. So you can say MSc equal to mean squared error ydf actual. So we'll give the value of actual values. It expects the actual and the predicted values. Okay, either we can do it manually by taking all these residuals and square it, or we can directly give this to the mean squared error. So this is my MSc value. So MSc value comes out with 2.54. Okay, but because it's a squared error, it is still a square term, isn't it? So MSc, if you look at it, it's still a square term. 1 by n summation of yi minus y hat square, still a square term. So very hard to interpret what the actual value is. So interpret what we do is, once you calculate MSc, we take a square root of it again to bring back to the original unit, right? RMSc, we call it a root mean squared error. This is called what? Root mean squared error. Okay, because there's a difference between the price. So at an average, what error we make in terms of price, we can get that. So this comes out to be, now there is no function to calculate RMSc, unfortunately. We can actually use RMSc np dot square root. There's a function called square root in numpy which can calculate the RMSc value. We take a square root of it, simple, and say that's my RMSc value. So 1.59. So what is RMSc 1.59 means? Intuitively, if you can try to understand this, of course it has a little more complexity to it, but if you try to understand this, when you use this model, the model of what? Price equal to 7.6 minus 4.9, sorry, 0.49 age, right? If you use this model and predict the price of the car, right? So there could be an average error of 1.59 lakh rupees. If the price, it says the car would be sold at 5 lakh rupees, to be plus 1.59 at an average. Okay, it's an average estimation. We'll look at little more interval to this later, but you can intuitively think like this, right? Plus or minus. Of course, it's a very large error interval. Our objective is to bring down this. Right? So if you say the car could be sold anywhere between 4.5 lakhs to, or you can say 3.5 lakhs to 6.5 lakhs. That's a very large interval, isn't it? So if you can bring down to something like, if the actual resale price of the car is 5, and you say the car can be sold anywhere between 4.5 to 5.5 lakhs, that still be okay, but not very large error interval. And which is fine, because we have only used age as a parameter to predict the price. But moment you add more factors, of course the accuracy of the model will also increase. But there is also another matrix called R square, which is can give you, in terms of how good the model is, uh, with a number between 0 to 1. You can think like a percentage. It's a 80% correct, 70% correct, or 100% correct, right? You can actually give a very absolute value of accuracy. It's called R square value, okay, which is calculated like this. uh, Imagine, if you think like, this is your price of the car, and this is age, right? Let's say, and the data of course looks something like this, right? As the age increases, the price reduces. Now, let's say you don't have the information of age, you only have the price of the cars. All that you have is what? Y, right? And of course the price are different prices. So what you do is, you find the variance in the price itself, the Y value, how much the Y is changing from the average value of Y. An average value is depicted like Y bar. You see, remember in the first few sessions we looked at that, right? So how much the Y value is varying, right, from the average value of Y. And then if you, of course, if you draw the perpendicular line from the data points, this will be the difference between the actual value and the Y average value. Now if you bring that information of age, right, so how much of these variations in the Y, the change in the price, can be explained through the age parameter. And then what you do is, we build a model like this, right, and then we calculate the error from the model, right, and then see, by bringing age as a variable, how much of total variance in the Y can be explained by this particular model, right? So it's almost like, Y is not a function of X, and Y equal to as a function of X. And we see, by bringing the the feature or factor to explain Y, how much of change in the variance, how much the variance in the Y, it can be explained. So you can think like Y equal to beta 0 plus beta 1 X plus error. Okay. So total variance in the Y, or total information in the Y, how much it can be explained by the model, and how much it cannot be explained by the model. That's error. So the total variance in the Y is 100, let's say, and the model is explaining only 80% of it and 20% remaining, right? So you can say it is 0.8. But if the model can only explain, let's say 20, and there's error 80, you can say the model's R square value is 0.2. Okay. So this is actually how much the model cannot explain unexplained variance divided by the total variance. And what's the total variance? Is nothing but my typical Ya minus Y bar average, right? And unexplained variance is my error, Yi minus the model, what's the error is. And the ratio is basically what? R square value. If in the model, right, there is no error, error is equal to 0. Okay, I built such a perfect model that the error is 0. That means what? My unexplained variance is 0, a total variance. Okay, so this is actually little changed. This has to be the explained variance. Okay, this is not unexplained variance, this is explained variance. That means my error is 0. So this, the R square value will be 1. But the error is, if I build a model, beta 0 plus beta 1x plus error, my error, whatever the y is, the model cannot explain everything, still the error is there, then of course it will be 0. So R square value range from 0 to 1 and commonly stated as a percentage in terms of 0 to 100. Of course, you will not have a model which is 0 and 100, which are extremely extreme cases. So what is a good R square value depends on the domain or context. In the field of social science, even a relatively low R square such as 0.5 could be considered relatively strong. Okay. Normally what we do is anything beyond 0.8 is called a very good model, 0.6 good model, all right. Anything less than that is not a good model, but that's again a thumb rule. You can have to understand this from the specific context. Like in other fields, standard R square is high. So for example, finance, R square value above 0.7 is also considered a very good correlation. But in healthcare, I think you have to have a very strong correlation. So you have to understand the context of the domain. You can always find some literature or published papers where what is typically accepted R square value. Based on that, you can take a call, it's a good model or a bad model. So how do you measure R square value here? In this case, what you can do is you can say from scikit-learn dot metrics import R square value. So R2 score, again it will take the actual value, the predicted value. Okay, this comes out to 0.52. So 50% variations in the price that we see in the car is because of the age information, right? Still it's okay, but you can always be increase that R square value with bringing it to other factors. Okay. So again, I'll quickly do a recap and we'll take the advanced part in the next session. Okay. So we loaded the data, final cars Maruti, and these are the factors and my outcome variable price. And for the first step, we have taken only one variable called age to predict the price value, and we see a negative correlation here. And we first build a simple linear regression, which is basically predicting the y value with respect to just one variable. And simple linear regression is given by y hat, which is a predicted value of y with respect to the x, equal to beta 0 plus beta 1x. This is your intercept and this is your regression coefficient. Okay, this is also called coefficient, but basically beta 0 is basically, it's called an intercept value. And you'll get some error which is calculated in terms of mean squared error, which is nothing but ya minus ya hat square. Then we set the value of x and y, what will my x value, what will my y value. Split the data into train and test. X-train and X-test, build the model, scikit-learn, linear model regression, and we found the intercept and coefficient. So once you build the model, you can predict on the test data and calculate RMSE, which gives you at an average how much error we make with respect to the actual value of the car. So we come to plus or minus 1.59 lakhs because this is YI minus. So this is the same unit as the Y. The RMSE has the same unit as what? Y value. So this is relative to the Y value. Okay. So don't consider model is a good and bad based on the scale of the value, because let's say you're building a model to predict the salary of a person, right? Based on the experience level or skill level and all that. Let's say you're actually doing it in terms of rupees, right? So let's say the RMSE comes out to 50,000. Not necessarily that means it's a bad model, right? It's basically saying the salary, what's the predicted value will be plus or minus 50,000 rupees. This could be a good model. So the scale of RMSE has to be understood from the scale of the Y. Okay. And then you take a call, it's a good or bad model. Just don't take it as a small value means it's good or large value means bad. Okay, it has to be with respect to the unit of the Y value. This is always a relative number, but R square is not relative number. R square is always a absolute number between 0 and 1, like I told you. So always give you a value between 0 and 1. The closer to 1, of course, is very good model. The closer to 0, anything between 0 to 0.5 is not a very good model at all. But again, I like told you, depends on the domain and the context. You can have to understand and take a judgment. Basically, it's a good or bad model. And the R square value here we calculate as to be what? 0.52. So this is of course not a good model, and we understand why, because we've taken only one particular variable to do that. Okay. So what I'll do is we will take a break today here, and we'll come back and look at multiple linear regression in the next session, and model deployment also. How do we store and deploy the model? And let me take any questions if you have for today's session.